Today's lesson deals with dilations. So you've heard of this term before. You've heard of dilating somebody's eye. When you dilate your eye, your pupil will enlarge so the doctor can see in it. So if you think about that pupil getting larger and smaller, that's a dilation. So what is a dilation? That is a reduction or enlargement of a figure. So it's a reduction or enlargement of a figure. The center of dilation is a more difficult topic to think about. If I say this is the center of dilation and I want to enlarge, we'll say this triangle. Maybe I want to enlarge it by a scale factor of 2. That means I'm going to double all the dimensions. So the neat thing is I can kind of look at this dimension and know that I need to double that. And that'll give me my new point. I need to look at this little dimension and I need to double it. That'll give me another new point. And I want to do this last one and double it. And there's that new point. So here's my new figure right here. So the center of dilation is this point out here. What's the book definition for that? Does anybody have a good book definition? Okay. So it's the point about which the figure is enlarged or reduced. Sometimes the center of dilation is outside the figure. Sometimes, though, it's inside the figure. So if it's inside, this smiley face, we'll say he has one eye, and I want to enlarge it, so everything enlarges. So that could be the center of dilation for that smiley face with a single eye. Another way to see it is go back to that little triangle. Sometimes it's inside. If we're going to double it again, we just take these distances and double them. There would be a center of dilation inside an object. You can also reduce them. So I could have started off with this big shape and reduced it by that same scale factor. So what's a scale factor? It's usually represented by the letter K. We've talked about this before. It's a number that you multiply all the coordinates by. So you're going to multiply all the coordinates by that number. So earlier I said I'm going to take these and double it. So everywhere I have that coordinate, I'm going to double it. And it's really, really easy on a graph. Next up, we got to talk about those words, reduction and enlargement. Whenever you reduce the size of something, you're going to be making it smaller. And when you enlarge it, you're going to be making it bigger. So these correspond to scale factors. Whenever you have a scale factor for a reduction, it's going to be less than 1. When you have a scale factor that's an enlargement, it's going to be greater than 1. So examples would be fractions for a reduction, like 1/2, 1/3, 2/5. Enlargement, you can still have fractions here, but it would be things like 4/3, 5/2, or you could have a scale factor of 2 or 10, things like that. Those would be examples of scale factors for enlargements and reductions. And the key thing that I also need to mention about a reduction is that it's not going to include 0. So it's only terms in between 0 and 1. Think about this. If a scale factor is 0, what happens when you multiply by 0? well, you go to nothing, so everything disappears. So we don't like that. Whenever you have a scale factor of 0, everything disappears, so you won't see that very often. What happens when you have a scale factor of exactly 1? No change. There's no change. It stays exactly the same size. It's good. Up next, we briefly talk about coordinate notation for a dilation. All it says is you take a point, and this is telling you that it's being dilated or being changed, and it becomes a different coordinate now when you multiply by k. So I'm taking x and multiplying by k. I'm taking y and multiplying by k. Here's an example. If I had the coordinate 3, 5, and a scale factor of, we'll say 3, that would translate to 3 times 3, comma, 3 times 5. Obviously, that simplifies, so you could have just said 3, 5 will dilate. I said translator. It dilates to 9, 15. So that is called coordinate notation for a dilation. So one more time. If k is between 0 and 1, we have a reduction. And if it's greater than 1, we have an enlargement. Example 1 says, draw dilation of this quadrilateral and then use a scale factor of 1/2 to see what the new shape is. So we're going to go through that together. We're going to graph these points, and then we're going to multiply everything by a scale factor of 1/2. So go ahead, take a little time, graph those points if you haven't already done so. All right, now that they're graphed, we can do the math. What we need to remember is that we need to take all the coordinates and multiply everything by 1/2. So we're going to do 1/2 times the x value, and then 1/2 times the y value. And this should be pretty quick. What's 1/2 of 2? Just 1. 1/2 of 0 is still 0. 1/2 of 6 is 3. 1/2 of -4 is -2. 1/2 of 8 is 4. 1/2 of 2 is 1. 1/2 of 6. 1/2 of 4. Now we have our new coordinates. Now there's one thing that I want to point out that I don't like about this problem, and this is kind of bad on their behalf. I don't like how they just created completely new names for these points. What they should have done is they should have called this A prime, B prime, C prime, and D prime. Please change that. So put those new letters out to the side and scribble out the other ones. Those are bad names. We know how to properly name these after a translation or dilation. And use the prime letters. The primes indicate that you have a new shape. So original has plain letters. The new shape has the prime letters. Now I can go through and we can graph those points. So now this blue shape with the prime letters, that's our new shape. And I can tell that it's gone from the plain letter down to the prime letter, so it's getting smaller. So this is obviously a reduction. And we can also see that it's a reduction by looking at the scale factor. This is a reduction. And sometimes they'll ask you this question. They'll say, find the center of dilation. And this is actually kind of neat how you find this. So whenever you're finding the center of dilation, all you need to do is trace the corresponding points back to their original spot. So I'm going to go from the plane B through the B prime, and I'm just going to pull it over this direction for a little while. I'm going to grab the C and go through the C prime and pull over this direction for a little while. D through the D prime, and then A through the A prime. Oops, I was a little off on that one. Let me try that one again. There's my undo. There it is. So once again, I have that last one, A, going through the A prime. And you should see that they all cross at what point? They all cross right here. And what's the ordered pair for that point? 0, 0. So what is the center of dilation? Okay, so write that out to the side. The center of dilation is the origin, 0, 0. On example 2, we have a triangle that we're going to graph, and then we're going to see, two triangles that we're going to graph. We're going to see, are these shapes similar? So this first part is pretty easy. You graph the original shape with the plain letters, and then you're going to graph the prime shape, which we found the coordinates by doing a multiplication of 2 by all the coordinates to get some new coordinates. But next it says verify that those triangles are similar. You need to remember that we had 3 ways to prove similarity. We had angle, angle, we had side, 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 and then we had side, angle, side. We need to pick one of the methods. I think 2 of them could be appropriate. I think one of these 2 would be appropriate because we can find the lengths of all the sides, and we can find the lengths of 2 sides and the angle in between at one of the vertices. Which one do we want to do? SAS is what I heard, so that's the one we'll focus on. We're going to focus on SAS. Now, what angle should we focus on? Those 90s. So we have to figure out and prove that these are 90-degree angles right here. So don't just say because they look like it. We got to prove that those are 90. How do you prove that you have perpendicular lines? I think I heard slope. Yeah. So slope. Whenever you have a vertical and horizontal line, you're always going to have opposite reciprocal slopes. So these slopes are opposite reciprocal. Slopes are opposite reciprocal. So that means the slope of C prime, B prime, is that slope undefined or 0? It's undefined. Think of this like a wall. Can you walk up a wall easily without any help? No, that's undefined. That's crazy. So that slope of this one is undefined. So the slope for CB is undefined. The slope for A prime, B prime is 0. Horizontal is 0. It's flat. It's like the ground. We can walk on the ground. Same kind of thing up here. Regular CB is going to be undefined. And then slope for AB is going to be 0. So those are always going to be opposite reciprocal when they're undefined and 0. So I did the angles. I can say the angle B corresponds and is congruent to angle B prime. Since they're not connected to anything, I can say those single letters. But now I got to prove those sides. And that's pretty easy. These are along the grid. So AB is how long? So AB is 2. And A prime, B prime is 4. 2/4 is 1/2. So we got to make sure this other one's 1/2. So the other one would be CB over C prime, B prime. And we're going to find that those are going to be 1, 2, 3, 4, 5. Is that 5? No, 6 over how many? Did I count wrong? 1, 2, 3 over 6. I did it backwards. 3 over 6 is also 1/2. Are these the same? Yes. And the other thing that a lot of people remember is that you can switch those to still say that they're proportionate. Just sometimes we do small over big, and that's okay. We would have 2 over 1, which goes back to that scale factor. So that proves side, angle, side. That's a full proof, and it verified that those triangles are similar. So we could have done side, 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 but we would have had that third side. We needed that third side. We could have found that with Pythagorean theorem, show that they still simplify to that same fraction, and be good from there. Example 3 is a very common problem. It says we're going to be finding a scale factor in this one. You're making your own photo magnets. Your photo is 8 inches by 10 inches. So I'm going to draw that to give you a picture to think about. I think this always helps. If you haven't been practicing this, you need to practice drawing pictures so you can see it better. The image on the magnet, though, is 2.8 by 3.5. So these are all in inches, so that makes it easy. What's the scale factor of the reduction? That's the key thing. So remember, what kind of range of values should a reduction be? So it should be from 0 to 1. It should be somewhere in there. So that means some kind of fraction probably. And typically, whenever we have a reduction, it's a small number over a bigger number for that reduction. So if I want to pick small over big, I need to put these numbers right here over these numbers. So 2.8 over 10. And simplify that. 2.8 over 10. Well, the problem is if you simplify it too much more, you're going to get some decimals. What I'm going to do is a little trick. I'm going to move this decimal over 1, and I'm going to move this decimal over 1. So that's 28 over 100. And now it's easier to simplify to a nice fraction. So half of 28 is 14. Half of 100 is 50. That's 7 over 25. The scale factor of that one is 7 over 20. I did notice that I made one little mistake. 2.8 doesn't correspond to 10. 2.8 corresponds to 8. So I need to modify this real quick. So instead of 28 over 100, it should be 28 over 80. So that'll be 40, and that'll be 20. So it's an easy fix. Sorry for that mistake. These pieces correspond. So make sure to pick corresponding parts. I'm now going to go to example 4 so we can finish this lesson. You want to create a quadrilateral JKLM similar to quadrilateral PQRS. What are the coordinates of M? So the key thing is to figure out which letters correspond. Right now I can see P corresponds to J, Q corresponds to K, and R corresponds to L. So make sure that you can see those corresponding points. I'll kind of color code them to try to help you out. And now, one little trick that I have for this deals with finding that center of dilation. So these trace back to here. These trace back to here. So you can see that the center of dilation is 0, 0. It's not always 0, 0, but frequently it is. The last thing that I would view is that from the center of dilation, going out through S, will eventually find us that new point. It's just figuring out how far out there it is. So what I would see is this. How long is this piece from the center of dilation to R? How many segments is that? That is over 2. Well, how far is it to go from there to L? 4. So how do you go from 2 to 4? You double everything. So let's find the coordinate for S. The coordinate for S is over 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. So if we're going to take S, which is 5, 5, and we're going to multiply everything by 2, it's pretty easy to do with mental math. I'll write it out. Whenever that changes with that scale factor of 2, what are our new coordinates? 10, 10. So, right here. Over 10, up 10. There's our new point. And I'll erase some of these other lines so you can see it a little better. So it's out here. So L goes up. And that new coordinate for M is 10, 10. There's our final answer. So quick reminder on this one. It didn't tell us the scale factor. We had to determine that ourselves. We found the scale factor by seeing how far it was from the center of origin. From the center of origin, center of dilation, it was from here to here, so that was 2 units. From the origin out to that point was 4 units. How do you go from 2 to 4? You multiply by 2. That told us our scale factor. You could have gone up this way as well. This goes 3 units, and then that goes 6 units. How do you go from 3 to 6? You multiply by 2. So that told us our scale factor. It is enlargement.